In this video, I'd like to talk about the goodness of the fit and how we can measure that. In order to see how we can measure the goodness of the fit, let's see first what actually is happening when we are conducting a regression analysis. So I'm assuming I have the sample of 4 data points here. And then we are assuming this is the best line, best linear equation that passes through all these data points, all right? Now, I'm just gonna pick this one, for example. So for this X, I'm gonna call this X, X1, X2, X3. I'm gonna call this X3, for example. And then for X3, I have one actual value of Y3 coming from my observation in my sample. So I have X3 and Y3, the actual value here. Also, if I have this, the equation of my regression line, I can find this point by plugging in. So if this is y hat equal to B0 plus B1x, if this is the equation of my estimated line, if I plug in X3, if I plug X3 into this equation, it is going to give me the value of y hat 3. So if I just record this number, it would be estimated value of y for this, for X3, if the value of my independent variable is equal to X3, my estimated value for Y will become Y hat 3. All right, so I have this two. So the difference between Y3 and Y hat 3 is called residual, as we already know. So I'm gonna use index I just to generalize it. EI is equal to YI minus Y hat I. Residual is equal, residual equals actual value of dependent variable minus estimated value of dependent variable at point xi. All right, so this is residual. And now if we take, so I have these 4 data points, 1, 2, 3, and 4 data points. If I take the average value for y, it's gonna happen to be, let's say this one, y hat being the average value of all these y. Y1, Y2, Y3, and Y4, if I take the average and call it y bar as the average of these data points. So this is y bar, Y3, y bar actually. So y bar is a fixed value regardless of the, it actually needs, for getting the y bar, we need to know, or we need to actually take into consideration all the values of yi's, right? So y bar will be sum of yi's divided by sample size. All right, now we have a relationship that always holds true regardless of these data points, how they're spread. So this is the relationship. If I take y minus y bar for any point, for any of these data points, squared, if I take the sum of squares of y minus y bar, It's actually y bar. There is no index I. Is equal to sum of y hat minus y bar squared plus sum of y minus y hat squared. So y minus y hat is equal to y minus, sum of squared of yi minus y bar is equal to sum of y minus y hat squared plus sum of y hat minus y bar squared, right? So this thing, it measures the total variation in y, the total variation in y, which we also call it SST, total sum of squares. And then this is called SSR, sum of squares due to regression. And this, the last one, is called SSE, sum of squares due to error. Due to error. And as you can see, all these values are going to be positive. So when you take sum of squares, it's going to be definitely either 0 or positive, right? And then because this relationship always holds true, SSR is going to be always less than or equal to SST. All right, so we can actually define coefficient of determination, or R squared, as SSR, the ratio of SSR with respect to SST. SSR divided by SST will be defined as coefficient of determination, and this value will always be between 0 and 1. So now let's see when this is equal to 1, when this is equal to 0. I'm going to go ahead and draw two simple scatter charts here again, two simple examples, X, Y. So if I have all my points, here, I mean, not all my points, none of my points actually were lying on the line, but let's see if everything falls on the line. Let's see what happens. So if I have this, what happens with SSE, SSR, SST? So what happens here in this case is perfect fit. So when I have perfect fit, what happens is that all my data points fall on the line. So they all follow the linear relationship, which means that yi is exactly equal to y hat I. The actual value is equal to the estimated value for each data point, 1, 2, 3, and 4, all right? So when this happens, when yi is equal to y hat I, and here I have indices, here also I have index. So when yi is equal to y hat I, what happens is that SSE becomes equal to 0. SSE is 0. There is no error. There is no error. So sum of squares due to error will be 0 when I have perfect fit. And as a result, SSR becomes equal to SST, which means that R squared is going to be exactly equal to 1. R squared equal to 1. So when I have perfect fit, when all these points fall on the line, I will have R squared equal to 1. I will have perfect fit. And that doesn't depend on the slope. So it can be negative slope, it can be positive slope, it can be a very strong slope, it can be, I mean, pretty close to flat, but still linear. As long as it's linear and as long as there is a persistent relationship, I will have a perfect fit and it will be a strong relationship, strong linear relationship, and I will get for a perfect fit, I will get a unity for R squared, all right? So this is one example, and now let's take a look at another extreme example, X, Y. So if I have my points like this, and my actual line is a flat line, completely horizontal line. What happens here is that this is Y hat, right? This is Y hat. So Y hat in this example is exactly equal to Y bar, the average value of Y. So this is no linear relationship, no linear relationship. So when I have no linear relationship, Y hat becomes equal to Y bar. The estimated value for each data point will become equal to the average Y. Basically, I can't explain the variation in Y using X, right? So that's what it means. So when Y hat is equal to Y bar, this means that SSR now is equal to 0. SSR 0, that means R squared is 0. So when I have no linear relationship, when my estimated line is like a flat line, a horizontal line, completely horizontal line, then I will have R squared equal to 0. Therefore, I use this actually to interpret the value of R squared. As R squared gets closer to 0, the relationship, the linear relationship gets weaker and weaker. And as R squared gets closer to 1, the relationship gets stronger and stronger. The linear relationship, the strength of relationship gets more powerful as R squared increases. So that is basically the goodness. This is how we get the goodness of the fit for linear regression. You can get it in 2 ways in Excel. So you can get it either from a scatter chart, add trend line, and then add R squared. Add equation and R squared, or you can get it from R squared from output or summary output of output tables of regression tool. When you run the regression tool from data analysis tool pack, at the first table in the summary output of the regression tool, you can see the R squared. R squared is given to you. This is R squared is what we use for measuring the strengths of the fit, but when we're dealing with multiple regression, there is actually another measure that is even more appropriate than R squared, and it's called adjusted R squared. I mean, it's a little above the scope of our course, but I'm just going to mention this because we are going to use it later on when we want to compare different multiple regression models, right? So adjusted R squared is even more accurate than R squared, and it takes into consideration the number of predictors. So when you have multiple regression variables, you don't want to just increase the number of variables in the model, because when you add a random variable, R squared is going to go up. Doesn't matter. I mean, when you add even a random variable to your regression model, R squared is going to go up. So you can prove that. But just to remove the effect of random variables into a model, we can use adjusted R squared. I'm just going to write down the formula. It's going to be 1 minus R squared times n minus 1 divided by n minus k minus 1, and n is sample size, and k is number of independent variables. You don't need to use this formula again. When you're using the regression tool, at the summary output in the first table, right below the R squared, you can see adjusted R squared. And that is usually when we are dealing with multiple regression. This is a much better measure for goodness of the fit.